tough time pronouncing his name. So he earned his Bachelor of Engineering in 1985 and Master of Engineering in 1987, and a PhD in 1990 in Electronic Engineering from the University of Pretoria, and a second PhD in 2000 in Theoretical Particle Physics from the University of Toronto in Canada. So it looks like he has crossed all the practical as well as abstract regimes of physics. He has been a faculty member at different universities: Potchefstroom, Ottawa, Pretoria, worked at government laboratories like Aerotech, today DPSS, and the National Laser Center, both part of CSIR, and spent 2 years in industry at JDS Uniphase Corporation in Canada. During most of his career, he worked on different fields in optics, especially diffractive optics, singular optics, statistical optics, optical fibers, periodic structures, and quantum optics. Currently, he's with the National Meteorology Institute of South Africa. So the title of his talk is Employing All Degrees of Freedom in Photonic Quantum State Preparation. So I'll not stand further between you and his interesting talk. So I'm going to switch off my video so you can pay attention to his talk. So let's hear you, sir.
Thank you very much for the very kind introduction. Yes, I'm going to talk about employing all the degrees of freedom in photonic quantum state preparation, and it will specifically deal with a Wigner functional approach for parametric down converted states. So spontaneous parametric down conversion is a process where you use a pump beam to illuminate a nonlinear crystal, and then some of the photons will be converted into a pair of photons that we call the signal and the idler. Now one may wonder that the or question, what is the nature of the quantum state that is produced, and in particular, what would be the Schmidt decomposition of such a state? Now you can address this to different communities. If you ask this to the continuous variable community, they'll probably tell you, well, the Schmidt bases are Fock states. So in other words, if you have in photons going one way, you will have in photons correlated with that going the other way. However, you can ask the same question to a different community, which focus on, for instance, the orbital angular momentum, which is a spatial temporal degree of freedom. In this case, if you focus only on the individual photons that's down converted, and you look at the modes, you will see that assuming that the incoming photon has 0 orbital angular momentum, the orbital angular momentum of the 2 down converted photons would be opposite. So the Schmidt decomposition for the OAM community would be represented as the opposite orbital angular momentum modes. So now you can ask, but what if I want to try and combine these spatial temporal degrees of freedom with the particle number degrees of freedom? Then maybe one can suggest something where you have n photons on one side with a particular mode, OAM mode, and on the other side you will have n photons with the opposite mode. But it doesn't take much to realize you can have more complicated situations where you have different modes for separate photons and then the complementary modes on the other side. So the situation becomes complicated, and what we need is a formalism that can incorporate the spatial temporal degrees of freedom and the particle number degrees of freedom, and preferably as continuous degrees of freedom in the Hilbert space for all the quantum optical states. Now I should point out there is a symplectic formalism that is continuous for the particle number degrees of freedom, but it is still discrete for the spatial temporal degrees of freedom because it typically represents that as discrete modes with a finite number. So what we're going to do is to consider the Moyle formalism, which has been developed by Moyle and Grunewald during the Second World War. In this formalism, states and operators are represented as quasi-probability distributions in phase space, and then the product of the operators are combined with the star product. An ideal quasi-probability distribution for this formalism is the Wigner function, which can be represented in this way. where you have the eigenstates of the quadrature operator shifted in different directions, contracted on some operator, in this case the density operator, and then it is Fourier transformed with respect to the shift to obtain a function of the quadrature variables which are analogous to the position and momentum of the harmonic oscillator. Now, this operator doesn't have to be the density operator, it can be any operator, and you can calculate a Wigner function for any operator. However, represented in this way, it only addresses the particle number degrees of freedom. To incorporate the spatial temporal degrees of freedom, we would want to generalize these quadrature bases. To do this, we consider the eigenvalue equation, where the quadrature operator is now a function of the wave vector, which is a three-dimensional vector. You can also think of it as the momentum vector. The eigenvalue is then a function also of this momentum vector. However, the eigenstates do not contain these momentum vectors explicitly. So what this implies is that for every function, for every eigenvalue function, there is a unique eigenstate. And because there are so many functions, you really have a vast space of eigenstates. Now, a similar equation applies for the P quadrature operator. The solution can be expressed in terms of an operator, an exponentiated operator, that operates on the vacuum state. And in this exponent, you find that the operators are defined in terms of integrals over the momentum space. They contain the creation operators, and then together with the eigenvalue function. There's also some strange operators which only contain the square of the creation operator, and then just the magnitude of the eigenvalue function. A similar solution applies for the P. Now, it turns out that these eigenstates form a orthogonal basis for the entire space. So, but in this case, the orthogonality condition is represented in terms of a Dirac delta functional, because these Q's are functions. And it also satisfies a completeness condition, but in this case, the completeness condition is represented in terms of a functional integral, because you integrate over all the functions that can be eigenvalue functions. So, and this identity is now the identity for the entire Hilbert space of quantum optical states. So we have here a complete orthogonal basis for the entire Hilbert space of quantum optical states. And we can now use that to generalize our Wigner function to become a Wigner functional. So we use these quadrature eigenstates, shift them, and then operate on the density matrix, which is now any density operator in our Hilbert space. And then the Fourier transform is a function of Fourier transform, because in the argument, these are now functions that are contracted on each other, which means that they are multiplied and integrated. And I'm going to use this diamond notation to represent such contractions throughout the rest of this talk. Just to show you something maybe more familiar, we can have a similar eigenvalue equation for coherent states, where you have the annihilation operator as a function of the wave vector, and then the complex valued function, which is the eigenvalue function, is the normal parameter function with which you would parameterize your coherent states. In this case, this complex valued eigenvalue function is related to the eigenvalue functions of the P and Q operators that I just shown you. And the Wigner functional for such a coherent state would be in this Gaussian form, but note that the argument is really an integral over functions, and it's not just variables, complex variables. And you can also then use these fixed spectrum coherent states to resolve the identity. In this case, the measure, the functional measure, incorporates a 1/2 pi, which indicates that it's an overall complete basis. So now we're going to use this formalism to study the parametric down-converted state. To do this, we follow an infinitesimal propagation approach. Now, it sounds very sophisticated, but it's really just the generalization of the Heisenberg equation, but instead of going in terms of time, we go here, take the derivative with respect to z, which is the propagation direction through the nonlinear crystal. And then you can see here, this is really just the commutator, but expressed in terms of these star products, and you can write these star products as integrals, as functional integrals. So, and then you would normally in a Heisenberg equation have the Hamiltonian here. Here you need a infinitesimal propagation operator, and we're going to represent that in terms of a generating function, which contains alpha as and beta as field variables for the down-converted fields and the pump fields respectively. And all these mu's are auxiliary field variables so that we can take functional derivatives with respect to them. And so we're going to generate the operator using a construction operator that consists of all these functional derivatives with respect to these auxiliary field variables. And in the construction operator, you would have these kernels. So it would be the T would be the kernel. It would be the 3-point vertex for the nonlinear process that produces the spontaneous parametric down conversion. And the P is just the linear propagation through the medium. So now, what will happen when we evaluate these integrals that represent the star products, it's going to transform the arguments of my Wigner function that represents the state here. And when I then apply the construction operator on that, it's going to produce function derivatives of the state. So in the end, what I get is the evolution equation in this form. Now it looks very nice and compact. If I wanted to write it out in terms of all the integrals, it will fill more than one this page. It will be a very, very complex expression. So what we have here is, you see the T's are the vertices, and it is contracted on twice or two down-converted field variables here, or maybe a functional derivative with respect to a field variable, and then the pump, the beta is the pump. So it's either a functional derivative with respect to the pump, or it is the pump field itself. Now I've removed the free space terms here, the free space propagation terms here, by going into a co-propagating frame. The effect of that is removed the P terms, and it attached or removed some free space propagation terms from these vertex kernels. So now, to make life a bit easier, because as you can imagine, that equation is a bit hard to solve. So what we're going to do is we're going to employ the semi-classical approximation. And for that purpose, we're going to assume that my state, which at this point incorporates both the down-converted fields and the pump fields, can be expressed in terms of a coherent state for the pump field times an unknown state for the down-converted fields. And the assumption now is that the pump will remain a coherent state. However, I allow the parameter function to evolve. So in other words, I can accommodate a depleting pump. In this case, the semi-classical approximation is not justified in the same way as people usually do it, by assuming that the pump remains undepleted. The only thing that I assume here is that the state remains a coherent state. And the benefit of that is that when I have a strong pump and I look at the situation on phase space, a coherent state is a minimum uncertainty state. So it has a very small size. When the pump is strong, then that coherent state is moved far away from the origin. So the width of the state on phase space is much, much smaller than the distance of the state from the origin. So we use this as a reason to approximate the pump now by the parameter function for the pump. So we replace the beta by beta 0, which is just the classical field that represents the pump. So this is where the semi-classical approximation now comes in. When we do this, our equation simplifies quite significantly. We only get these two terms that survive. And you can see now that the vertex is contracted with this classical field, and it then forms a bilinear kernel. And then we can solve this. And we get a solution that in terms of the Wigner function, it is basically the pure squeezed vacuum state, the Wigner function of which has this form. So in the argument, we have A and B's are the kernels. And what we're going to do is we're going to assume that we can use a Magnus expansion for this term. And so that these kernel functions become sequences of the contractions of these H's. And the H's is simply just the bilinear kernel that I get when I contract the classical field for the pump on the vertex. And so you can see I get all these sequences of more and more contractions. This Z is just a Z ordering, which has to do with the Z arguments here. Now I'm going to employ another simplification, which is quite valid in most experiments, and that is where we assume that the pump beam has a Rayleigh range that is much longer than the length of the nonlinear crystal. In that case, the H bilinear kernels become independent of Z, and so I can evaluate all these Z integrals, and I just get these factors. So now I can sum this sequence, at least formally, to obtain a functional version of the hyperbolic cosine function with the H in the argument, and in the B case, it's the hyperbolic sine function. And these are familiar in terms of these solutions. So now I'm going to use this solution to study the squeezing in the state. Now, to observe the squeezing, I want to measure the variance in the quadrature. So my variance is given in terms of the second and first moments with respect to some generalized quadrature operator. And the measurements are made with the aid of a homodyne experiment, and the operator for the homodyne experiment can be expressed as this generalized quadrature operator contracted with the magnitude of the mode of my local oscillator. So the local oscillator has a magnitude and a phase. The phase determines the direction of my quadrature operator in phase space. In terms of a Wigner function, Wigner functional, the homodyne operator becomes this expression. Now, to make my life easier, I'm going to express this as a generating function. So in this generating function, I put the Wigner function for the homodyne operator in the exponent together with a generating parameter, and then I multiply that with my down-converted field, and then I integrate that. And then I obtain a generating function for which, if I take the derivatives with respect to this generating parameter, I can obtain the first and second moments, and then I can use that to construct my variance. So we apply this to the SPDC state, and we find that the first moment is 0, which is not a surprise because a vacuum, squeezed vacuum is centered at the origin. The second moment is then given in terms of this, where I have substituted in this the kernels of my SPDC state, and it's contracted with the modes of the local oscillator. Now I can evaluate this to all orders in the Magnus expansion, and the result I then get for my squeezing operator is given in this form. So you can see the summation over n, it runs over all the terms in the Magnus expansion. And I have 3 parameters here. This capital C is the squeezing parameter, and it's just a combination of all the dimension parameters in the experiment that determines the efficiency of the down conversion process. Then I also have a small c, which is the squared ratio of the bandwidths of the pump and the local oscillator. And the tau is the square ratio of the beam width of the local oscillator and the pump. And now what I can do is to study the effects of the bandwidth and the mode sizes on squeezing. Now, the standard result I will get when both these parameters go to 0. So in other words, in the case of the C, it means that the pump bandwidth is much smaller than the local oscillator bandwidth. And in the case of the tau, it is the local oscillator beam width that is much smaller than the pump beam width. In that case, I get the standard result. So in the two principal directions, I get the typical squeezing behavior where one is expanded and one is decreased as a function of the squeezing parameter. If we now look at the effect of the mode size, we still let this small c go to 0 for the bandwidth, but now the mode sizes, we allow arbitrary values. And then we get this expression, which we can sum to form a hypergeometrical function. And I will show you the curves for these in a moment. If we study the bandwidth case, in this case, I allow xi to be an arbitrary value, but I still allow tau to go to 0. Now I get a summation that I cannot sum. However, you can use some simplifications here, and you can then show that the result of this is that the squeezing is reduced. So to look at the effect of the mode size, if my tau is a very small parameter, then I get this the normal squeezing behavior. Remember, this is logarithmic on the vertical axis, so it looks like a linear decrease that I would get as I'm increasing my squeezing parameter. But as I increase this tau parameter, so this ratio of the mode sizes, I see that I have a reduced squeezing. And if the tau is about 10, there's almost no squeezing going on anymore. A better way maybe to look at this is to look at the minimum uncertainty or the uncertainty area, which I get by multiplying the standard deviations in the two directions. For a minimum uncertainty state, the value I should get is a half. And we can see that when the tau is very small, it is a half and it remains more or less a half regardless of the squeezing parameter. But as I'm increasing tau, I see that I start to increase the minimum uncertainty area. So I lose the minimum uncertainty property. The interesting thing is that it's not a monotonous change. If I plot this as a function of tau, of this beam ratio, I see that my minimum uncertainty area, or my uncertainty area, increases to some maximum value, and then it starts to decrease again. The reason for that is not quite clear to me at the moment. So then I go to the entanglement and study the entanglement in the SPDC state. To do that, we have to look at a bipartite squeezed vacuum state. So we want to make the, use some post-processing to make the signal and the idlers apparent. So in this case, alpha is maybe the signal beam and beta is the idler beam. So assuming that it is a pure state, I can then do the partial trace, which is the functional integral over one of these, let's say the idler beam. The result then gives me the Wigner functional that typically looks like that of a thermal state. And then I calculate the purity of this partial trace, which is just the square of this function integrated over the remaining field variable. The result is the inverse of the full Schmidt number, which gives me the inverse of the determinant. So in other words, the Schmidt number is equal to the determinant of the one kernel function. And I can express such a determinant as the exponent of the trace of the functional logarithm of that kernel function, which is in this case the cosine function. That L is the length of the crystal. Now this is difficult to solve. Again, we have to make some approximations, typically the thin crystal approximation. And then with the result that we get for this full Schmidt number as a function of the basically the squeezing parameter, which is here expressed as the enhanced cross-section. The cross-section is the way that we express the efficiency of the nonlinear process. Enhancement you get by increasing the power in the pump. And here we plot this as on a logarithmic curve. And we see a very rapid, drastic increase in the full-Schmidt number, which is a way to quantify the entanglement in a pure state. And this is the full-Schmidt number because it incorporates all the degrees of freedom, the particle number degrees of freedom, and the spatial temporal degrees of freedom. Please note this is a logarithmic scale, so this is really a very drastic increase. So then finally, let me just conclude by saying that I've showed you that the eigenstates of the momentum-dependent quadrature operators represent complete orthogonal bases, and this would then allow us to formalize a Wigner functional formalism for the operators and states in a Hilbert space of all the quantum optical states, which incorporates all the particle number degrees of freedom and spatial temporal degrees of freedom. And now this formalism has been used here to obtain the spontaneous parametric down-converted state in all degrees of freedom. Now, when I say all degrees of freedom, I haven't mentioned polarization in this talk, but you can also incorporate polarization quite readily. It's just that it becomes more complicated. For instance, to obtain a bipartite state, you could have used type 2 down conversion, and then you can use a polarizing beam splitter to separate the signal from the either beam. Okay. So with the aid of this down-converted state, I then could study the local oscillator, the effect of the local oscillator mode size and bandwidth on the observed squeezing. And I could also study the entanglement in all the degrees of freedom. Thank you very much.
Okay, that was a very interesting talk. It's full of information. Now the Zoom is open for questions. You can turn on your video and ask the questions, or raise your hand, whichever way you feel.
Stop this.
I think Thomas has raised the hand here.
Okay, could you please ask your question, Dr. Thomas?
Hello, Steph.
Hi, Thomas.
Yes, thank you. Thank you for the nice talk. It's amazing how much progress you made since I last saw you. And I just want to know, your last result talks about the entanglement that you produce in the idler and the signal. Sorry, the idler and the signal beam, and it looks like the Schmidt number is increasing faster than exponentially, right?
Yes.
So this is very nice. I mean, this would be very nice, but I didn't understand. You know, you had on the x-axis you had the enhanced cross-section,
Yes.
and I didn't understand what that actually is. So how, with what variable does it increase exponentially or faster?
So that is basically your squeezing parameter. So I expressed it in terms of the enhanced cross-section. So the cross-section, you can express the nonlinear coefficient of the parametric down conversion process as a cross-section. In other words, a little cross-section area. It's like a scattering cross-section. Now to enhance it, you multiply that with the alpha of the coherent state of your pump. Basically, the modulus, the absolute value of that. So it is basically the square root of the number of photons that the pump contains. Yeah. So let me just comment on that extreme or stronger than exponential growth. Remember, to make this calculation, I had to employ some approximations and some simplifications. So in the paper, I show, of course, the detail of all these approximations. And then I argue that I can trust the curve up to a certain point. Beyond that point, my approximation, the validity of the approximation becomes questionable. So in other words, I cannot guarantee that this growth will be maintained. And I argue also that I expect it to slow down when the rate at which the entanglement increases start to outpace the rate at which down-converted photons are added. So in other words, it should at some point saturate, but I can't, I'm not able in my calculation to obtain that point.
Yes, but may I ask, I mean, the main point is the intensity of the pump beam. So if you increase the intensity of the pump beam, you can for a certain kind of area, you can expect that it increases very, very rapidly.
Yes.
Right, that the entanglement increases very rapidly. And I mean, that would be very good news, because I mean, that's exactly the resource we would need, you know, I guess. Thank you very much.
How to use it is a different question.
Maybe one more. Can I ask one more? And namely, is it, can you distinguish, how do you distinguish the idler from the signal beam? I mean, is there a degree of freedom that?
Yeah, I alluded to that in the talk. So what I used in the calculation was the assumption of type 2 down conversion. So type 2 down conversion tags, remember you didn't like the tagging, but tags the idler and the signal with different polarizations. And then you can use a polarizing beam splitter to separate them.
Okay.
Yeah.
Thank you.
Okay.
Professor Aosi. Professor Dios.
Yeah, thank you. Yeah, can you hear me?
Yes.
Can you hear me? Staff, yes. Thank you for this very clear, perfect presentation. I have a more abstract comment than Conrad's was. Wigner functions or Wigner functionals are famously indefinite. They may have negative parts. Now, in addition to the Moyal-Grunewald invention, or beyond that, there is another approach which is based on the Q function and the so-called Husimi function. The Husimi function, which is a smeared version of the Wigner function, is always non-negative, which opens some new perspectives, opens the door to a statistical interpretation of the phase-space distribution. So my question, do you have any comment or idea about a version of your construction which is based on the Husimi function?
I can say that in the same way that you can transform Wigner functions to Husimi functions, maybe using the characteristic function, you can also transform Wigner functionals to Husimi functionals using a Wigner functional. So the same analogous, I've worked through the same analogous transformations and they work. So in other words, one should maybe not call it a Wigner functional formalism, but just a functional phase-space formalism, because any of these distributions can be used in your calculations, whatever you find convenient. I happen to like the Wigner functions, that's why I use Wigner functions. There's no funniness in converting between the operator and the Wigner function. Whereas for other distributions, you get these singularities and things like that that you run into. So okay, maybe not with your Husimi function, but I know with the P representation, things can become very, very singular. I also want to add about the infinities. I can bring my talk up again if you want to, but in it I have, for instance, in the expression for the Wigner functional for the coherent state, I have shown you a normalization constant. That constant is formally divergent. Now, of course, it becomes an issue if you don't keep track of them very carefully. But I can now state that I have checked whenever I calculate a physical observable, all these infinities cancel. So I'm quite happy to say that in the beginning, I just swept them under the rug. But in the meantime, I've checked more carefully, and I'm quite satisfied that provided that you're very careful, you find that they do cancel exactly whenever you calculate an observable quantity.
Okay, thanks.
There's a question from Dr. Sarang Bonsley. He wants to know what are the complications after you include polarization, if you could elaborate a bit on that.
The complications. Okay, so the benefit of the polarization is that it's a two-dimensional space. So assuming we have a paraxial beam, we can always just have a two-dimensional space. So in other words, what will happen is our quantities will contain an additional index. So instead of I don't know whether I should go back to my talk. Should I just show you?
Yeah, go ahead.
Maybe, let me see if I can I share the screen again? How do I share the screen? So I just want to go back to all the way back to So here I have the definition of the contraction, which is in this case ignoring the polarization, and only it becomes an integral over the momentum. When you do have the polarization, then you will have an additional index that is sitting here. And so this contraction will then also include a summation over that spin index. But apart from that little complication, the formalism goes through exactly in the same way.
Any other questions? If not, let's thank the speaker for a very crisp and nice talk. And feel free to type the questions while the session is going on, so he can try to answer. Just write down the speaker's name so they know whom it is addressed to. So let me check if Dr. Vibhor Singh has joined. Vibhor, have you joined?
Hi, Anand. Are you able to hear me?
Yeah, you can turn on your video to say hi.
Yeah.
Hi. So it's a pleasure to introduce Vibhor Singh. He's an assistant professor at the Department of Physics, IISc Bangalore. His focus of his group is on superconducting devices based on emerging quantum technologies. Currently, he's indulged in various activities such as cavity optomechanics in microwave domain, superconducting materials for quantum devices, circuit QED systems, superconducting qubit-based hybrid optomechanical systems. So the talk he has chosen today is quite exciting. It's coupling an electromechanical device with a transmon qubit. Transmon qubits themselves are a subject of very large study. So I'm eager to hear what he's about to talk. So I'll switch off my video so Vibhor can start his talk.
Yeah. So thanks, Anand, for the kind introduction. I hope you are able to see my screen.
Yeah, it's good.
Okay, great. So let me begin thanking organizers for giving me this opportunity to present our research work here. And I would also like to thank the funding agencies who give us money to do this research. So like you said, title for today's talk is Electromechanical Device with a Transmon Qubit. And the title may seem very technical. I'll try to, keep the talk accessible to a broader audience without getting into too much technicalities. But at any point, if there are questions, feel free to interrupt me and, raise hand or type. Okay. So the work, of course, is done in collaboration with my PhD students and postdocs. The work today I'm going to present is largely led by Tanmay Bera and Saurav Majumdar. Okay, so let me begin first showing a one-slide introduction to circuit QED. So circuit QED is a field analogous to cavity QED, which describes the interaction of atoms with the electromagnetic modes. Here, the role of optical cavity is played by these electrical LC circuits. So one can write down the Hamiltonian for these electrical circuits and see that because of the symmetry in charge and flux, you get these equispaced energy levels. Okay, so the eigenstates of a linear oscillator are equispaced. In order to form artificial atoms such as superconducting qubits, you make these oscillators nonlinear. So superconducting qubits such as transmon is nothing but a nonlinear oscillator. And the nonlinearity is brought in by replacing this linear inductor by what is called Josephson junction. The free energy of Josephson junction is given by this cosine function. It's EJ times cosine phi, okay, where phi is the superconducting phase difference. So the moment you deviate from this nice symmetry between charge and magnetic flux, you lose this very beautiful equispaced energy levels, and we have now unequispaced energy levels. Okay, and at sufficiently low temperatures, you can have the system in the quantum ground state of this potential well, and restrict yourself only to 2 levels. Okay, and this is what we refer as a qubit. But any point is important to remember that these qubits are multi-level. Harmonic oscillators. Okay, so typically these electrical circuits, they are designed to operate in few gigahertz frequency range. Once you are cooled down to very low temperatures such as 10 millikelvin, they are naturally initialized to quantum ground state, so most of the thermal noise disappears. Typically these are made from superconductors, so you can achieve very high quality factors, something order like 1 million or so. Okay, by coupling these electrical circuits together through circuit elements such as capacitor or inductors, one can achieve coupling between them. So by using a capacitor, one can achieve a transverse coupling, which will let you swap excitation between electrical cavity and this transmon, which is a superconducting qubit. Okay. So this circuit QED platform is a fairly well matured technology and has wide applications in quantum computing and peripheral devices. And one point that I would like to make here is that the excitations which are used in circuit QED platform, they are the excitations of electromagnetic modes. They are photons in some sense. Okay. And given the maturity of this platform, researchers now are asking questions that, can we bring in new degrees of freedom and integrate circuit QED platform there? Okay, and the general philosophy behind integrating these new degrees of freedom is that to use, properties which gives complementary advantages. Okay, so on this slide, what I have is 3 examples. One which is dubbed as quantum magnonics. Okay, so what we do here is you have this circuit QED platform in 3D architecture. And you can bring in, ferromagnetic insulators and spin excitations of those. Okay, so those are called magnons, and study the interaction between magnons and single excitation of the qubit. Okay, so one can also, due to the high frequency of these magnons, you can have a coherent exchange, quantum coherent exchange of excitation from spin degree of freedom to the excitation in the qubit. The second example is quantum acoustodynamics. It's a derivative of circuit QED, except that the role of photons is now played by phonons, which are formed by the standing wave on the surface of this piezoelectric substrate. And you can combine qubits in this architecture and have the same Jaynes-Cummings kind of interaction between phonons and excitation in the superconducting qubit. The fact that speed of sound is much smaller than the speed of light, these devices offers completely new type of interesting experiments which are currently outside the realm of circuit QED. Okay. The third example that I have taken is from cavity optomechanics, where we have vibrating mechanical oscillators made in this drum shape, and these oscillators can be used to capture single propagating photons. Okay, so you can have the information stored into mechanical vibration for some time and then retrieve it later. So typically the fluctual modes of these mechanical resonators are at low frequency and they have a very high resurgence, rethermalization time. So you can have the information stored in the vibrational modes for very long time and then retrieve it later. So whenever you're thinking of hybrid devices, bringing in more degrees of freedom and utilizing the circuit QED platform, what is important to pay attention to the figure of merits, which are typically involved coupling strength and the coherence rate of all the degrees of freedoms that we introduce. Okay, so there's a very nice review article which is given here that can be read for more details. Okay, so typically the other component that I'm going to focus in my talk, apart from circuit QED, are these nanomechanical resonators. So the talk is going to be integrating these nanomechanical resonator to circuit QED platform. So just a quick introduction to these mechanical resonators. So what you see in this image is these beam-shaped mechanical resonator of silicon nitride. They can have two type of modes, in plane and out of plane modes when they vibrate. Typically, frequency of these modes are in the range of 1 megahertz to 100 megahertz. Once they are cooled down to very low temperature, like 10 millikelvin, most of the thermal fluctuation is gone. So you have thermal fluctuation, which are order of 10 to the power minus 13 meter per square root hertz. And if you compare those with the quantum zero point motion of these mechanical resonators, they are an order of magnitude larger. Okay, so most of the thermal energy is gone, but still there are some thermal phonons which are left even at very low temperatures, and they are typically order 50 to 500. Okay, so the question that we try to address in our group is, can we introduce a circuit QED platform with these mechanical oscillators and control the quantum states of these massive oscillators beyond the quantum ground state? Okay, so that's a bigger question that we are trying to address. So one way you can couple mechanical oscillator to electrical circuits is by having these mechanically compliant capacitors. Okay, so what you see in this picture, there is this disc-shaped object, which is a parallel plate capacitor, and the top plate of this capacitor is free to vibrate. Okay, it is shunted by a big inductor, which is in this meander form, and thus you form a LC circuit. Okay, so you can design the frequency of this LC circuit in microwave domain, and as this capacitor vibrates, the mechanical resonator vibrates, there will be a shift in the cavity frequency, which can be used to have these two modes coupled together, one electrical and one mechanical. So this is how you can understand the coupling, that now we have a capacitor which is displacement dependent. So the capacitance depends on the separation between the plates of these of this capacitor. So if we change X, omega C is going to be changed. Okay. So this modulation of capacitance results into a modulation of cavity frequency. And one natural way of defining the optomechanical coupling in such a system would be through this radiation pressure coupling, where intensity of microwave in this LC oscillator couples to displacement. Okay. And the figure of merit, which is single photon coupling strength, can be defined as a shift in cavity frequency due to the quantum zero point motion of this mechanical oscillator. Okay. So this is one way of realizing optomechanical coupling between electromagnetic mode and mechanical oscillator. If you think hard about it, you would see that actually this coupling between mechanical mode and electromagnetic cavity is mediated by charge degree of freedom. Okay. While you look at the Hamiltonian for a simple LC oscillator, you have 2 degrees of freedom available to you. This charge, another is magnetic flux, and these are conjugate variables. Okay. What we try to address in our lab is that, can we use the flux degree of freedom to make a similar optomechanical system? And utilizing this idea, we want to go beyond. Okay, we want to address questions like, would it be possible to actually integrate a circuit QED platform in it? Okay, so we are looking for an equivalent circuit, but where the modulation of inductance comes from the displacement of mechanical resonator. Okay. So how do we do this? How do we make a displacement dependent inductor? So the idea comes from the squid loop, the working of squid loop. So a squid loop is basically 2 Josephson junction placed in a loop. Okay. So what happens for such an electrical circuit? The inductance of this component is dependent on magnetic flux, which is threaded by this loop. Okay. And one can work out the formula for inductance, and it's given by this complicated looking relation here. What you can notice here, so maybe a few points, the I naught here is the critical current of each junction. and phi is the flux which is threaded by the squid loop, and phi naught is the magnetic flux quantum. Okay, so what you notice in this expression that we have a situation where inductance of such a loop is enharmonic. What I mean by that, typically if when you consider a linear inductor, Lj is just a parameter of geometry, shape of the conducting loop. But here what we have is inductance depends on the magnetic flux value. So that makes it enharmonic, okay? More than that, it is actually periodic, and the periodicity is half flux quantum because of this absolute function coming in here. And since it is made from superconductors, it's an example of a dissipationless inductor. So a squid loop is essentially a dissipationless, nonlinear, periodic inductor, okay? So now that we see that inductance depends on magnetic flux, which is passing through this loop, it's easy to see how to make a displacement dependent inductor. What we do, we make one of the arm of this squid loop suspended, okay? Now the magnetic flux value passing through this loop will depend on the displacement of this wire, okay? And therefore the inductance value of this loop would get linked to the displacement of the wire, okay? So this is the way you can realize a displacement dependent inductor. Okay, so next question we wanted to ask that would it be possible to design a transmon qubit with such a displacement dependent inductor? And the answer is of course yes. So the implementation in device is done in the following way, that we take this squid loop and shunt it with a capacitor here so that we get a transmon mode. There are several things that you have to keep in mind while designing such a circuit, that while you are shunting it with a capacitance, you maintain sufficient enharmonicity so that individual levels, when you quantize such a circuit, can be addressed, and we can treat this circuit effectively like a transmon, okay? So for the readout of this qubit, what we do, we couple it to a linear cavity in the form of a 3D microwave cavity. I'll show some pictures later. And then this 3D microwave cavity is integrated with input and output ports for the readout of qubit. Okay, so this is a schematic of the device, how the transmon is coupled to the cavity. So unlike conventional transmons where you have two capacitive pads and junction sitting in between, we modify this design slightly and bring in the squid loop in the recess in the cavity wall. And we can also introduce a low frequency RF driveline if we want to actuate the mechanical resonator. Okay. So this is how the pattern device looks like on a silicon nitride substrate. This tiny electrode, what you see here, that's the capacitor, which is going to shunt this squid inductance. The tiny this plus-like shape that you see here, that is the squid loop. And inside we have these Josephson junctions and the suspended mechanical oscillator. Other two electrodes, what we have here, they are just for the performing input and output and applying gate voltages if needed. Okay, so this is the schematic of the device. This is a zoom in when we zoom in close to the squid loop. So here you can clearly see the suspended mechanical resonator along with two Josephson junction. Okay, so this is what is forming as a squid loop. This electrode runs up and forms the capacitance necessary to make this transmon qubit. This T-shaped electrode that you see, that is for mechanical actuation if you want to add. The mechanical oscillator that you see here is something like 45 micron in length and has 300 nanometer width and about 100 nanometer thickness. Materials used are aluminum and silicon nitride. So we have silicon nitride underneath, and on top we have patterned aluminum to have the Josephson junction and squid loop formed. Okay. So this is the device we have. Then this device sits inside a 3D microwave cavity. This is a copper 3D microwave cavity. And then we have input-output ports and an actuation port here. Okay. The entire cavity goes inside dilution fridge, okay, where we have a small magnet to apply magnetic field and to flux bias such a device. And then, this entire thing cools down to 10 millikelvin, okay, with the push of a button. All right, so let me summarize the device that I just introduced, what we have, okay? So what we are looking at is a flux tunable qubit, and it has been designed at a frequency of 8 gigahertz, and it couples to a cavity mode through this typical Rabi coupling, transverse coupling, and the cavity frequency is designed to be 6 gigahertz mode. To interact with the qubit, we can interact in two different ways. We can send in microwaves to the cavity, and this is basically a photon field, and look at the output that comes out. Okay. As a part of this flux qubit, we have a mechanical mode, which is designed close to 6 megahertz frequency. And due to this, it's part of this quick coupling, we have a longitudinal coupling between mechanical resonator and the qubit mode, okay? And in addition, we also have a mechanical drive line on the mechanical resonator, which is equivalent to a phonon field if you want to use it, okay? So looking at it from two perspectives, you can think of it as a tunable frequency two-level system, which has both phonon modes, okay, which is similar to a trapped ion system. Or if you want to think it from a mechanical perspective, then we have a mechanical resonator, which has an internal degree of freedom, which is in half, okay. So this, except this coupling is longitudinal, the system is very much similar to a trapped ion system, if you want to make analogs. All right, so with such a device in mind, then we proceed to perform measurements and try to characterize coupling, optomechanical coupling between transmon and mechanical oscillator. Okay, so the first simple experiment that we can do is, we try to understand, the qubit, we try to characterize qubit and mechanical oscillators. So for this, we perform single tone spectroscopy. What I mean by that we send in microwave through one port and try to measure transmission through the cavity as we change the magnetic flux. Okay, so this is an experimental result. What you see here is transmission through the cavity as the magnetic flux is varied. Okay, so what we see at close to zero magnetic flux, we have a transmission maximum. So red here means a large transmission and blue means very small transmission. So we have a peak in transmission around 6 gigahertz, and that's the rest cavity frequency. Okay, and as magnetic flux is increased, the qubit mode, which is designed around 8 gigahertz, comes from top, and this qubit mode is changing again. I want to remind the dependence of squid inductance on magnetic flux. Okay, so as we increase magnetic flux, the squid inductance goes up, and hence qubit frequency goes down. And it's periodic in half flux quantum, so it will be minimum at 0.5. So qubit mode comes from some high frequency, and as we increase flux, it becomes resonant with the cavity, and due to the strong coupling between transmon qubit and 3D cavity, we have these avoided crossing. Okay, and then you can continue increasing the flux. Qubit mode will go to a very low frequency, and due to its periodicity on magnetic flux, it will come back again and go to a maximum. So this pattern of avoided crossing will repeat itself as we increase the magnetic flux. Okay, so such measurements are helpful because they allow us to characterize the qubit and cavity system. So we have a qubit mode, which is around 8 gigahertz in frequency, and a bare cavity frequency of 6 gigahertz. If we take a line cut, a line plot at 0.33 phi naught, then we can have both the rest eigenstates seen clearly. And from the separation of these two, we can establish the qubit cavity coupling of about 85 megahertz. Okay, so these are, if you want to call that, the qubit and qton type of modes. Okay, so near resonance, these two are hybridized. Okay, so the magnetic field which is applied in this case is perpendicular to the plane of the squid loop. So, since magnetic field is perpendicular to squid loop, we will be sensitive to the in-plane mode of vibration. Okay, so before I get to the point where I want to explain how to do characterization of mechanical resonator, let's take a look at a better look at understanding the optomechanical coupling in this system. Okay, so it turns out that the optomechanical coupling in this system is proportional to the total flux which is applied. Okay, or I'll put it alternatively, how many magnetic flux quantum are threaded by this squid loop. And it's quite easy to understand that if we apply a large magnetic field and hence a large flux, then a small change in the displacement would result into a larger modulating flux, and hence larger shift in the rest mode frequency. Okay, so this optomechanical coupling here is defined as the shift in the rest mode frequency due to 0-point motion. And like I said, if you apply large magnetic field, then a small change in displacement would cause a larger change in flux, and hence a larger optomechanical coupling. So optomechanical coupling in the system scales with magnetic field, or put it differently, it scales with the number of quantum that are passing through the squid loop. So if we try to do this single tone spectroscopy of qubit mode in different lobes where we have large magnetic flux applied, it's better to have done such experiments, in like where you can apply maximum field, so that optomechanical coupling can be increased. Okay, So to characterize mechanical resonator, what we do, we bias the system somewhere here in some higher magnetic flux lobe, and where the slope of this dressed mode is higher. Okay. So if you, for example, bias here, you get no optomechanical coupling because here the cavity frequency is flux insensitive. But if you park it here where the slope is maximum, you will get a large optomechanical coupling. Okay. So what we do in order to characterize mechanical resonator, we send in a microwave tone here at one of these slopes and try to measure the phase noise in the outcoming microwave. Okay. So what you see on this color plot is a power spectral density of the microwave noise, which is coming out from the system as it is driven on one of these higher slopes of dress mode. Okay. In this one, the sensitivity, as you would see shortly, the optomechanical coupling is so high that we could do, single shot measurements of thermal noise and could plot the histogram. If you have seen thermal motion, typically, in such devices, you would see average value, but because of large coupling, we could do single shot measurements and could see the thermal motion in histograms also. Okay. What you see on the right-hand side is the average plot computed from these histograms. And, from here, we can characterize a mechanical frequency of something like 6.5 megahertz and a line width of 6 hertz, which corresponds to a quality factor of over a million. Okay. One nice thing about these thermal motion is that it allows us to calibrate the mechanical coupling rate. And like I said earlier, this optomechanical coupling rate is a function of magnetic flux. So as we increase the magnetic flux, we can achieve optomechanical coupling rate G plus of something like 4 kilohertz. Okay. And this is only by applying a magnetic field of 3.7 millitesla, which is the upper limit in our experiment that we could do. In principle, one can apply 10 times more magnetic field and have much larger coupling. Okay. So this number may not make a lot of sense, how big 4 kilohertz is in comparison to other numbers. So just to put it in perspective, based on this capacitive coupling scheme that I showed earlier, with just a drum type of a capacitor, this is almost an order of magnitude increase in optomechanical coupling rate. Okay, and in principle, there is a scope of increasing it further by applying larger magnetic field. Okay, so we have large coupling between transmon and mechanical resonator. What is the consequence of it? Okay, so this is the next question that we try to address. So one thing that I would like to stress here is that the 4 kilohertz coupling that we have obtained is actually nearly resonant. What I mean by that, we choose an operation point, magnetic flux operation point, when the qubit and cavity modes are in resonance. So what you see on this plot are the eigenvalues of the system, right, as qubit frequency is tuned. Okay, so the 4 kilohertz coupling we obtain is somewhere here where the slope of these rest mode is somewhat smaller. In principle, if you detune the qubit further away, you can operate at a much larger slope of frequency with respect to flux and get much larger coupling. This disadvantage, of course, of such an approach would be that now the cavity mode is more or less flat, so you can't do a direct single tone spectroscopy on it. Okay, so you have to resort to some kind of a two-tone spectroscopy to establish electromechanical coupling. Okay. And since these two modes can be dispersively tuned, we don't have to deal with hybridized states. We can directly define a qubit, a direct coupling between qubit and the mechanical oscillator. Okay. So by tuning the qubit almost a gigahertz away from the cavity mode, we could enhance the qubit mechanical coupling rate up to 40 kilohertz. Okay. And because of this large optomechanical coupling rate of 40 kilohertz, we see some nice features. Okay. So when we carry out spectroscopy measurements on qubit, what we see that as we increase the optomechanical coupling, the qubit spectrum splits into two peaks, and in between there are multiple fringes. Okay, so as we go from bottom to top, the term which is EM here indicating the optomechanical coupling rate is increasing. Okay, so this system here, what we are looking at is a two-level system like the transmon qubit, which is driven simultaneously in longitudinal and transverse directions. So let me maybe spend a minute here to tell you what the measurement you are looking at. So like I said in the previous slide, the qubit is detuned far away from the cavity, and we are performing a two-tone spectroscopy. So in two-tone spectroscopy, what we do, we look at the cavity's transmission while driving a probe tone near the qubit frequency. Okay, so this probe tone necessarily causes Rabi flops between ground and the first excited states. So that shows up as here, and the strength of the probe tone is ES. Okay. In addition, what we have is a frequency fluctuation of this transmon qubit because of a mechanical resonator being present. Okay, so that degree of part of the physics is coming in this sinusoidal modulation that we have put in here. Okay, so if, for example, optomechanical coupling is 0, if we set EM to 0, we have a standard sigma z by 2, which is the qubit and the Rabi flopping on it. But in addition, what we have of usual qubit frequency, we have the fluctuations which are harmonic. Okay, so such a system has been studied by Landau-Zehner and further later by Stickelberg, and I think even Majorana studied this system. It turns out it doesn't have any analytical solution for the most general case, and one has to resort to numerics to get the eigenvalues. Okay, and the splitting of this qubit spectrum comes out from the fact that, you know, if you just consider a qubit with a transverse drive, then you can imagine that, you know, the system is undergoing through these avoided crossing regions multiple times. Okay, and depending on how fast it's causing, you can cause transition from one quasi-energy to another quasi-energy. And in between, it accumulate phase, which is referred as a Steckelberg phase. And due to this accumulated phase, there could be an interference that would shows up in qubit spectrum. So these weak fringes that we observe here, they are coming from the interference from the phase that system has accumulated while going from one quasi-energy to another qubit quasi-energy. These interference pattern, it's nicely reproduced by the theory. So this has come using solving master equations and putting this Hamiltonian in. The contrast of these fringes is not very good. That's partly because the T2 time in our experiments is smaller than the time period of the mechanical oscillator. So if we could improve the coherence dephasing time, then, you know, these fringes would become much better. Okay. So with this slide, I will, I suppose, stop here, just bring the summary for the talk. So what I showed you is that, you know, we have a flux coupled hybrid device where qubit is coupled to a mechanical oscillator. We can achieve, you know, qubit mechanical oscillator coupling rate up to 40 kilohertz. And as a consequence of that, we observe Landau-Zehner Steckelberg interference. Okay. As an outlook, what we are aiming in the current experiment, we had a qubit line width of 12 megahertz and a mechanical frequency of 6.5 megahertz. So this puts us into sideband unresolved limit. So we can't do nice cooling type of experiments where you can pump the system at a sideband and try to remove excess thermal phonons. Okay. So what we want to work in future is to reduce the qubit line width so that we can, or increase the mechanical frequency so that we can get into resolved sideband limit, and then we can use different protocols once the system is initialized, once the mechanical resonator is initialized in the quantum ground state. Okay. So with that, I would like to thank you. So I would also like to point out this paper that we have put on archive. So if you want to see details, you are most welcome to go through this archive preprint. And yeah, thank you for your kind attention. I'll stop here.
Questions from the audience first? Anyone from the audience?
Yes, I have a question.
Yeah, go ahead, please. You can.
So, hi Vibhor, it was a fantastic talk. I have this small question. Since we have this mechanical oscillators which are quantum, is it possible to couple them first of all? And if we can couple them, then can we use them like what we have this optical modes, right? We have this boson sampling kind of problems. Okay, so can we perform those algorithms, those protocols on these mechanical oscillators?
It's an interesting question. So interaction-wise, I would say, achieving beam splitter-like interaction, which is at the heart of boson sampling problem,
Right.
should not be difficult. The problem I see is, when you fabricate mechanical oscillators, you have to, for a boson sampling problem, you have to have multiple mechanical oscillators and have them coupled through beam splitter-like interaction, if I understand your question correctly.
Right.
So designing their frequencies to be identical, it's a big challenge. Okay, so every time we design a mechanical oscillator, its frequency will be slightly different than what we intend it to be.
By at least a percentage.
Yeah, there might be some clever ways. I need to think about it. It's an interesting question.
And how do we actually create the oscillator coupling?
I'm sorry, please say it again.
Like if we want to couple two oscillators, how do we go about that?
So there are different ways. One of the example I have it here. So like this transverse Rabi coupling. Okay, so this is between two electrical circuits, but you can make a mechanical analog also. So here what happens that you try to, if you think about it, how this transverse Rabi coupling has come because voltage 0 point fluctuation of this oscillator here. I hope you can see my cursor.
Yes.
They are driving a current through the junction. Okay. So that's what result into transverse Rabi coupling. And for example, if you want to design a longitudinal coupling, you can have the 0 point fluctuations in this oscillator have changed the frequency of this blue resonator. Okay, so that can be done again by designing it through a squid loop. So there are ways by which you can achieve transverse or Rabi coupling between electrical circuits. And for mechanical oscillator, I suppose in dispersal limit through sideband pumping, it would naturally be a transverse coupling.
Okay, thank you.
Yeah.
Okay, I have a few questions, Vibhor.
Yeah, please go ahead.
So is your qubit also partially suspended? You think that's the source of broader line width?
It's a good question. Qubit is partly suspended, yes, but I would expect that to actually help in terms of line width.
From the TLS systems.
From the TLS point of view, what we are doing is we are removing most of the dielectric. So this, I did not get into too much of fabrication details, but this qubit is patterned on top of silicon nitride, and it's well-known material with lots of TLSs. So we were not expecting very high T1 or T2 for this qubit because partly it's patterned on silicon nitride. Although when we do fabrication, we try to remove silicon nitride, but the one which is below aluminum, you can't get rid of it.
Yeah.
So I would expect that suspension is perhaps not causing the loss of coherence. It's the silicon nitride.
But might use other modes, right? Very high frequency modes.
So electrical modes should not be there because electrical modes are something that we can see in simulations very well.
Okay. And you're coupling by electric field to your cavity?
That is right.
Okay. So, and your mechanical mode is on the sideways, right? On the plane of the...
Yeah, it is in the same plane as the qubit capacitor.
Okay, this is one question my microwaves course students should ask if they are in the audience. Why have you gone to 3D cavities instead of CPW cavities?
It's just ease of fabrication, right? Our device is already so complicated that the yields are low. And
no, it's actually like
CPW cavity on top, then it makes the fabrication more complex. 3D cavities, for example, I can get them machined in a workshop, and just every time you just have to clean them and they are good to go.
No, but it's kind of like reinventing old things in a very nice way, right? Because you don't even find them in textbooks nowadays very easily.
Yeah.
So you'll have to look up the formulas and model them and get them back. So
that is right.
Yeah. So, but so you don't suffer from a lower loss in the Q of the 3D cavity, or you get a very high Q in the cavity also?
So this is the experiment demands that we should apply magnetic field, and then the choice of material for 3D cavity is only copper.
Okay.
Right. So then there are of course resistive losses in copper, and typically you get like a 2 megahertz line width for a copper cavity at millikelvin, and that's what we also observe.
Okay, there's a hand risen by Manabendra. Manabendra, could you
Yes.
ask your question, please?
Thank you, Vibhor, for this interesting talk. So I have some general question in a sense, because you kind of have like one qubit you couple with a bosonic field. So how easy it is to tune the coupling strength? For example, you are having this James coming kind of interaction there. So how is it? I mean, this is the first question. And second is that, can I also make this coupling non-linear? For example, let's say intensity dependent coupling and so on.
Yeah.
Okay. And third is that if I go for two photon kind of interaction, like you have for Raman case, or there are several processes, no, where you have like two photon transition or interaction and so. So all these things, if I ask how easy it is to implement in your method.
Yeah. So to answer first question, so I mean, actually, to answer most of your questions, so one of the big advantage that you have with these superconducting devices is that if you write down some Hamiltonian, you can really tailor it according to your needs. Okay. So now to address individually, so this tunable coupling, transverse Rabi coupling that you said, right? Is it tunable? The answer is yes, but then this capacitor type approach is not the way to go. Okay, so if you want to have a tunable coupling between a bosonic mode and a qubit, then one has to go through some kind of a tunable junction-based approach. But the idea would be same, that eventually you should design the system in a way that it's the field operator that comes in a product. Okay, and then when you quantize it, it will become a transverse Rabi coupling. So the answer to first question is yes, you can design systems with tunable transverse coupling. But what I showed you here, that's not the answer. To answer your second question, whether you can achieve nonlinear coupling terms, yes, absolutely. In fact, we are doing some experiments now where in the same experiment, we can achieve transverse and longitudinal and higher order couplings, which couples to like A dagger A square. Okay. So those type of couplings are also possible. Sorry, I forgot the last thing you said about two photon interaction. What was the specific question?
So essentially, so normally there are situations where we have this Raman kind of transition. So you have two levels. So let's consider instead of qubit, you have qubit.
Yeah. So yeah. So two photon processes, they happens all the time at high powers. What I have here is a sort of a simplified form of transverse coupling. Okay, this is all after making the rotating wave approximation. But in general, what you have is a dipole moment coupling to A plus A dagger, right? And if you don't make transverse this approximation, you can have G to be very large, where you can see effects of two photon processes also.
And it's easy. So I could imagine it's possible. My question was how easy it is in terms of your way.
So it's difficult for me to answer without knowing the actual Hamiltonian you have in mind. So typically the strategy people follow, if you have some custom Hamiltonian and you want to engineer it with superconducting components, is you can take two approaches. You can have all the nonlinearities placed in the circuit in a static form using junctions, or you can try to engineer it with parametric pumps. Okay. So unless you clarify what Hamiltonian you have in mind, it's going to be difficult for me to give a general answer.
Okay. So it's okay. I got more or less.
These things are doable through static, design of nonlinearity or by parametric pumps.
Yeah. I understand it. So it's more like this EIT kind of thing I was mentioning to go. It's like a coherent driving.
Yeah, that's right. Yeah.
Okay, I got the answer. Thank you so much. Thank you.
I think he also had some papers on EIT in the past. You might be interested in looking at that.
Yeah, right. Those were more, I think, in optomechanical conventional without qubit being there. Yeah.
Okay.
So there is one question by Dr. Ranjit. wants to know what is the current extent of scalability of these hybrid systems. What is the number of maximum oscillators that can be coupled together in a single step so far? Has anyone done that? I think that's what he wants to know.
Yeah, so I mean, we are trying to do some prototyping type of experiment. Let one device work first, and and we can show that it's possible to cool down to quantum ground state and realize analogous physics like we have in trapped ion. So we are working at a single device level. But I don't see, like you mentioned earlier, there is no difficulty in going for a planar version of such devices. So you can use CPW cavities and have those coupled to qubit and mechanical oscillators. Once you switch to 2D, scaling should not be a problem, as I see. But with 3D, of course, the limitations from the physical size of the cavity would always be there.
So are you planning to do any nonlinearity of your beam by applying gate voltage or something? Of course, you can't be in the ground state when you probe them.
It's an interesting question. So we are not looking into that direction because most of the time, the estimates we get for mechanical nonlinearity, they seem to be very small. So they are far away from single phonon level. And, then most of the nonlinear physics is sort of a well understood, I would say, in mechanical oscillators, unless you really push it into quantum limits. So we are not trying to look into that direction.
You need a Duffing system at 0 point energy, right? That's not.
That is right. That is absolutely right. And that seemed to be extremely challenging.
Yeah, that has from the materials point.
Yeah.
Any other questions, please? Okay, let's thank the speaker for a very entertaining talk. Lots of nice devices. And I think we had 2 short sessions with good interactions. Now let me introduce the next speaker. The next speaker is Dr. Rakesh Kumar Singh. He's an associate professor at IIT PHU. He also served an assistant and associate professor at Indian Institute of Space and Technology, India. Singh received his master's degree from BHU and PhD from IIT Delhi. He worked as a postdoctoral researcher at University of Oulu, Finland, and at the University of Electromechanical, Tokyo as a JSPS postdoctoral fellow. He's a senior member of the Optical Society of America, life member of the Optical Society of India, and member of the SPI. His interests are in fundamental and applied optics, and research works cover structure, light, interferometry, digital holography, coherence in optics, computational optics, instrumentation with chaotic light, polarization optics, and classical quantum optics for imaging. He has published more than 60 papers in international journals of repute. So let me welcome Professor Rakesh Singh to present his work.
Okay, thank you very much.
The topic he's presenting is ghost imaging. Yeah.
Am I audible?
Yeah, you're audible, sir.
Okay, thank you very much for the introduction. And I would like to thank the organizer for giving me this opportunity to share my work on phase recovery and the ghost imaging. So the idea is that the ghost imaging is a kind of, if you see the research work going on in this area, people in both in classical and quantum domains are working on the unconventional imaging techniques like ghost imaging. There are several unconventional imaging. So in this particular talk, I would like to first briefly tell about the fundamental of correlation imaging or unconventional imaging, and then I will go to the ghost imaging. And particularly on the issue of the phase recovery. That is a very challenging issue, particularly on the correlation-based imaging techniques. So this is outline of my talk, where I will explain the fundamental aspects, particularly on the interferometry, and then what happens if I consider that if I try to extend this interferometry to the vectorial domain. Though in this particular talk, I will concentrate only on the scalar domain, but I will try to cover that how to extend the interferometry to the polarized light and then we can extend our imaging techniques to the polarization domain, or we can say we can develop vectorial correlation imaging techniques. And to answer this question, I will try to connect with low and higher order correlations, where the polarization, particularly in the higher order correlations, correlation plays a very critical role. And in this context, we'll discuss the fundamental physics aspects and also the applied aspects. Particularly, I will concentrate on the imaging applications. There are plenty of applications, but in this particular talk, I will discuss only the imaging applications. And after that, I will try to connect the variety of correlation techniques and how these correlation techniques, how the ghost imaging is connected with these correlation techniques. And major emphasis will be on the extending the idea of the ghost imaging to the holographic domain, the holography approach, so we can recover the phase part in the ghost imaging. And then I will conclude my talk. So when we talk the imaging, particularly I will concentrate in the visible domain. Choice of radiation plays very important role. But I would like to emphasize here that though we are concentrating the ghost imaging in the visible domain, but if you for the students, if you see the literature, this kind of idea is extended to the different range of radiation. So it's not only in the visible domain. This kind of idea is very commonly used in other range of wavelength. Okay. So now I'm posing a question. What is is it any difference between seeing and imaging? So why I am posing this question, I will try to explain in the next slide. So when we say the image formation or seeing any object, we see the object by usually we consider a lens, and then we consider the diffraction limited imaging condition. Now the question is that why we get the diffraction limited condition, because and this is connected with the size of the imaging for image forming lens. Now, so to understand the image formation, there are several parameters of the light which plays important role. Here I will consider only amplitude, phase, and then coherence. There are other parameters, particularly if you are interested to develop an imaging system for polarization, we have to include the polarization feature of the polarization parameter of the light, but that makes system complicated. But as we know that in many research areas or in many practical applications, polarization gives the high contrast imaging, particularly in the imaging of the biological objects. We can get the better image, high contrast image, even in the strain-free images with high contrast if we use the polarization sensitive camera or polarization sensitive devices. Unfortunately, if you consider the simplest detector, like our eye is a detector, but it never it doesn't give the polarization information. So to get the polarization information of the sample or the light, we have to design a system which offers the polarization part. And in my talk, I will try to connect, I will not present, but I will try to connect how we can extend the correlation imaging techniques, particularly for even the ghost imaging to the polarization domain. So I will consider here mainly the interference, amplitude, phase, because interference is anyway being influenced by the structured light, which we design by manipulating or tailoring the amplitude, phase information of the light, particularly when we talk in the coherence domain. But when we go to the generic domain, we can also play with the coherence of the light. Okay. So there are many ways to play with the coherence of the light, but in this particular talk, I will concentrate only on the amplitude and phase. So let me try to connect with the characteristic of the light, particularly how different parameters of the light affects the interference or propagation. Because when we consider the diffraction of the light, the fundamental parameters of the light, particularly the amplitude, phase, and wavelength, those things affects your diffraction pattern and the interference. Nowadays, a lot of discussion is being going on to incorporate the effect of the polarization in the interference. If you see the earlier work, people usually considered the uniform polarization, or they try to connect the fringe visibility only with the coherence. But if you consider a situation where the polarization is inhomogeneous or non-uniform, in that case, it's very difficult to connect with only connect the fringe visibility only with a coherence or scalar coherence. So I'll try to answer or try to just explain how the polarization connects or how the polarization affects the interference fringe visibility and what will be its impact on the imaging. So now, so to incorporate the polarization effect in the broad perspective, we have to deal with a more generalized coherence theory, and people called it the uniform theory of coherence and polarization. So let us consider that if I consider the two orthogonal bases, x and y. So in this case, the one of the coherence correlation function or coherence matrix elements I just represented here. We have the 2x2. I'm considering only the transverse field. So in this particular case, we'll have the 2x2 coherence matrix elements. If I consider the scalar case, then I can assume that all elements of the coherence matrix are same. So I will mainly deal with, when I will deal with a scalar case, I will consider this this kind of model and demonstrate some of our experimental results. If anybody is interested to know about the role of polarization on the interference fringe visibility or the higher order correlation, I will share some of our results, just details of our publications, and you can go through it. So when we calculate the correlation function, usually in the experiment we replace the ensemble average by either by time average, but here we some of our works we also replace ensemble average by spatial average under certain circumstances. I will explain that condition. Okay. So when we talk the interference, this is a very fundamental and very basic experiments which gives you the idea of the nature of the light. So the fringe visibility tells you what kind of light you are considering through these two pinholes, Q1 and Q2. And these two lights, I mean, from the nature of the light will decide the fringe visibility. But what happens if is it possible to extend, or is it possible to cover that even coherence and polarization both in the interference, conventional interference approach? The answer is no, because we are considering, usually when we consider the interference, we usually consider the interference in the context of only intensity modulation. Like, for example, I wrote this equation I, which is given as a function of the spatial coherence function, or the coherence function, the correlation between 2 point sources Q1 and Q2. But what happens, just if I pose a question, what happens if we have the two orthogonally polarized light? Suppose you have X polarized light through a pinhole Q1 and Y polarized light through a pinhole Q2. But these two orthogonally polarized light you have designed in such a way that they are coming from the same coherent source, and now we have flipped their polarization state. So if you consider the usual interference pattern based on the intensity modulation like I wrote here in this slide, so you will observe that there is no fringe. So this will be a kind of contradiction of your experimental reality. So usually conventionally when we define the coherence or when we analyze the interference fringe visibility, we say that we'll get the for fully coherent case we'll get the high v equal to 1, the fringe visibility 1, and then for incoherent light it will become 0. But when I go to the the question I just raised, when I go to the interference of orthogonally polarized light, we never get any contrast in the interference pattern. But we know that the source which we are considering is a fully coherent. So to answer these questions, a lot of work is going on presently, a lot of discussion also to give a proper definition of the degree of coherence and polarization. So few definitions have come in recent years. So I will not go to the definitions. I will just try to connect that. If I just try to say that rather than only measuring the intensity pattern, if you are able to measure all Stokes parameters, or if you are able to capture 4 Stokes parameter, you will be able to observe the modulation in one of two, at least two of the orthogonal, at least two of the Stokes parameters. So the problem was that the information was missing in the intensity modulation, but there is certain information encoded into the other Stokes parameters. And if you are able to capture those information, we can develop or we can observe the effect of the interference of two orthogonal polarization components. So based on this, we have recently developed a technique called Stokes holography, where we have utilized the interference of the polarized light and measuring the different Stokes parameters. You can encode information and then reconstruct it. But encoding little bit challenging, because either you need a material which records all the Stokes parameter, or you need some kind of other process. But to overcome this difficulty, we came with the idea to use the random scattering. So you allow your light, polarized light, to interfere over the random scattering medium and then allow to pass. And then you have the random process or stochastic light, and then try to use the correlation properties and reconstruct the object. So that is the idea, how to extend or how to use the polarization interferometry in the image. So these are few this area is very interesting, particularly in the context of both fundamental and then applied domains. So like I was mentioning here that we have like this technique, what we call the lensless Stokes holography with a Hanbury-Brown twist approach. I will try to discuss the Hanbury-Brown and then just briefly tell how we can extend this Hanbury-Brown to the polarization domain. Because if you see the conventional Hanbury-Brown, people usually talk the scalar in the scalar context. Okay. Now, when we try to understand the imaging system with the correlation optics, so one of the fundamentals, a very important relation in the correlation optics is the Van-Sitter-Zernike theorem, which connects your incoherent source with the far-field correlation function. The temporal counterpart of the Van-Sitter-Zernike theorem is also possible, but right now, here in my talk, I'm discussing only the spatial coherence. There are a temporal version of Van-Sitter-Zernike theorem, but I'm not going to that. So there are many applications of this correlation imaging system, like what we call the Michelson stellar interferometer and photon correlation holography, and ghost imaging also connected with correlation techniques. So what is Hanbury-Brown twist approach or intensity interferometer? So this was proposed in different contexts, but we are trying to use the Hanbury-Brown twist approach in designing a different kind of imaging system. So if you're considering the light source here, if you see this figure, and if you detect the light by two detectors, and if you correlate it, the correlation properties of intensity, particularly the intensity correlation. Intensity correlation here is connected with the second order correlation. So when I say intensity correlation, I mean to say the fourth order correlation. So the intensity correlation, which I wrote delta I R1 into delta I R2 left hand side, that is nothing but the modulus square of the coherence function. And if you go to my previous slide, I told the coherence function is nothing but a Fourier transform of your incoherent source. So although this relation, the Hanbury-Brown twist approach offers you the it connects you with the spectrum of the object, but the phase information is lost. Why? Because we are getting only the modulus part of the coherence function. So this is the kind of phase recovery problem usually we face in the we see in the coherent optics in the context of imaging. Like if you have certain object and illuminating that object with a coherent light and putting a detector at a certain distance, your detector will give only the intensity measurement, and in that case your phase is lost. So because if I want to completely recover the object, I need to have the phase information of the object. So to overcome this problem, some people use the iterative methods, but in this particular talk, I will discuss how to recover this kind of phase, or how to overcome the phase problem in the Henry-Brown twist approach using the interferometry. Okay. So these are few these are a few works which we have recently done on the Henry-Brown twist approach with the phase shifting, and next applied this for the imaging of the complex valued object and even the polarized object. In comparison, there is a well-known fact that in comparison to the usual young slit experiment or field-based interferometer, the Henry-Brown twist interferometer or intensity interferometers are more stable. Even if you do the experiment with a non-vibrating table, even if in the highly disturbing environment, you will get the better result in comparison to the field-based interferometer. The idea is that this is a well-known fact, and we have also utilized this fact of this feature of the Henry-Brown twist experiment to develop a new quantitative imaging system using the holography, like in these two papers. Okay. So the ghost imaging. So ghost imaging is also a part of the correlation-based imaging system. So if you see the figure here, if you consider a laser, and so if you consider the laser beam is passing through a diffuser which generates a kind of thermal light source, and this light is being divided into two parts by a beam splitter. One part of the light goes to illuminate the object, which is represented by a spatial object. So when I say what is a spatial object, I mean to say the object which is having some spatially varying values. It's not binary object. Okay. So I will try to demonstrate in my work that we have considered very generic object. It's not binary object like 0 and pi or 0 or 1. So we are considering a very generic object. So the light which interacts with the object, it will go to the bucket detector, and then other part of the light which was reflected by beam splitter will go to the camera, CCD, kind of array of detectors. And then when you correlate, the correlation of these two light from the two different paths will give you the information of the object. The temporal version of the ghost imaging is also available, but we are concentrating, or we are doing work mainly, presently we are doing only on the spatial domain, or you can say the spatial version of the ghost imaging. So the how we get the, because if you see here, the numerator here in the quantity CR is nothing but the quantity which we got in the HBTX approach. So nothing but the correlation of the intensity. Okay. Gently, people are also trying to extend the ghost imaging to the computational ghost imaging. And these are very beautiful review article by Sapiro Group, where they try to extend cover the ghost imaging from quantum to classical to computational. And my work is also trying to, we are trying to extend or develop a ghost imaging with a computational approach. Rather than using the rotational ground glass, we can use the device called spatial light modulator. I will explain this in the coming slides, to generate a thermal light source and then use this for the correlation-based imaging and ghost imaging. The quantum source people have also used, like I have shown here. And this has also, like quantum versus classical, this has generated a lot of interest and discussion in the research community. And people are demonstrating this kind of, though there will be certain issue on the visibility of the reconstructed image, but I'm not going to that aspect. I will try to cover only the implementation or realization of the ghost imaging with the classical source. So let us consider this particular, the first figure. So source is classical or quantum, whatever you're considering. And then like I mentioned in previous slide, one part of the beam goes to the bucket detector after interaction with through the object, and the second part without interacting with the object goes to the pinhole detector, and then you measure the correlation, and with the correlation we try to recover the object. So in this case, because this technique is all based on the Hanbury-Brown twist approach, so definitely we face the problem of the phase loss, or what we call the phase recovery. So like I mentioned in the context of the Hanbury-Brown twist experiment, exact same thing, because the ghost imaging is based on the correlation or Hanbury-Brown intensity correlation. So in this case, if you follow the conventional Hanbury-Brown twist approach, the phase part is lost. So we try to recover I will explain how we can get the phase recovery. So I'm trying to solve this problem. One approach, like I mentioned here, that you measure the information here at the diffraction pattern and do the iteration. And from the iteration, using the optimization approach, you can get the sample information. But there are certain limitations in the iterative approach. So in our work, rather than going to the iteration, we use the interferometric approach to solve the phase problem and get the quantity Fk rather than modulus of Fk. Okay. So phase recovery is very commonly a well-known problem, even the coherent optics and the optics based on the correlation techniques. So a research group led by Professor Gori tried to propose a problem, try to give a solution to overcome the phase recovery. And this idea, like the experimental setup I presented here, this is based on the second order correlation measurement. So if you see here, this is the G is a rotating ground glass, and the light from this G is illuminating your object F, and this is now being divided into the two portion and going through the single slit and then try to measure the interference in visibility. However, the limitation of this kind of interferometer, because if you want the 2D image of the object, you need to scan the entire object, because if you use the conventional young slit approach, you need to scan the entire object, and that is a time consuming. This is one issue. Another issue is that the system is unstable. I mean, if you have any disturbance external, if you don't have the vibration isolation table, or if you have some kind of disturbance, your result will be affected. So what is solution? We try to propose overcome this issue using the intensity correlation rather than the field correlation. So this technique we call the ghost diffraction holographic microscope. So I will explain what is this technique. Okay. So when we say so if I just try to summarize what I described earlier, so this was the first picture A is the Hanbury-Brown twist scheme. Here I just showed one detector. The center pixel of the detector will be suppose I1, and the remaining other pixel you can say the I2. And then I will take the ensemble, correlate, and then take the ensemble average. So this is the usually we do in the conventional HBT approach. And then next, if I connect with the ghost imaging approach, which I just explained, the next the ghost imaging techniques I can easily explain using this diagram. So here you can see the light I'm considering incoherent light, and then this incoherent light is being divided into two parts. One part is going through the object, and object is a complex. Please remember, object is a complex. When I say complex, I mean to say it is having both amplitude and phase. We can extend to the correlation, but right now I'm considering only amplitude and phase. And then other part is not going to the without interfering, without going through the object, is being detected by detector D2. So if I do the correlation of the information from the detector D1 and D2, intensity detector from D1 and D2, we can get the modulus square of the object. So since the object is a complex, so the phase information will be lost. For example, if I have the spiral phase plate which generates a vortex, or if I have the vortex beam which is having a certain helical phase structure, if I use this kind of the technique which I just presented in figure B, this will not give me the phase info. This technique will not offer the phase information of the object. So we will not be able to say what is topological charge of the vortex or what is the mode number. Okay, what is the azimuthal mode? I'm talking about azimuthal. You can also extend to the radial mode, but here I'm just concentrating on the azimuthal because it's saying that it's representing the phase structure. So to solve this problem, what we did, we extended the idea of interferometry here in the ghost imaging. So see here, so you have now, if you compare the figure B and figure C, what you have, we allowed another reference random field, what we call the homegrown random field. So you can consider that you have the incoherent light is coming in the top, and then illuminating your object. One portion, second portion is a reference, and then your third, and you have the third being what you call the reference random field, and this reference random field is going towards port detector. Since this reference field is completely independent from the first source, so there will be no correlation between these two light sources. So their cross correlation, when you find the intensity correlation, their cross correlation term will cancel out. So if I use this feature, I can develop a holographic imaging system. So what we get, this will offer you the intensity correlation between these two detectors will give you kind of interference fringes, or what we call the hologram in intensity correlation. So in comparison to the usual Hanbury-Brown twist experiment, here you will get the fringes in the intensity correlation, and once you have the fringes, you can do the Fourier processing and get back the object. So I will show how we get this object from the correlation of these raw images. So camera image in D1 and camera image in D2. Another uniqueness of our work is that we have implemented this technique with a frozen random light. Means usually we rotate the ground glass and then do the temporal averaging. What we have done, the rotating ground glass movement was freezed, and then we detected the random pattern, static random pattern, and then we replaced the ensemble average by spatial averaging rather than the time average. So you can consider like this. You have the two detectors. Your light is coming fluctuating, and then you are measuring by two detectors correlating, and the next time another correlation, and then you are averaging. We are not doing like this in this particular work. What we are doing, the light which is a wide detected by the camera, which is having the bigger large number of pixels. So it detected one camera is here, other camera is here. So I will fix this center pixel of this camera and then correlate with other camera intensity values, and then take the spatial averaging. Means I will move in the space and do the averaging. So this will give you this will offer you complete complex field from a only from two intensity pattern. No need to do the integration. Okay. So what is the basic principle? How we explain this? The formation of the fringes in the intensity correlation. So when we consider the light propagation from here, we can use a propagation kernel. Like from beam splitter, we have the object, and then light from this object propagates to the camera plane. Similarly here, the other light U2, which is propagating without interaction of the from the object. So we can represent this complex field U1 and U2, and UR is your reference. So propagation of the light from the object to the camera plane is represented by a propagation kernel HL, and L here is the reference and object. And if I just take the correlation, since we know that these two, the random field UR and U1 and U2, UR is completely different from the random field which is illuminating your object and making a reference. So when we take the correlation, the cross correlation between UR and U1, U2 will be 0. And when you calculate the correlation, your correlation will be it will give you a relation like G equal to interference of two quantities, G, capital G, and G R. So it's a coherence interference between two coherence functions. So it's very similar to what we observe in the holography. Like in holography, what do? we consider the beam which we want to image, or we consider the information or sample beam, and then interfere that sample beam with a reference beam. So here reference beam is GR and my sample beam is GG. And when we take the, here if you consider the modulus square, this will give you the 4 terms, and this will be exactly similar to the holographic terms which you get for the complex field U. But here this kind of similar kind of holographic term you are getting for G in intensity correlation. So you can see there is a similarity between what you get in the U and what you get in the G. And these are well known because if you see the work of Professor Emil Wolf, he has done tremendous work on the particularly seminal work on the comparison between optical field and then coherence function has contributed significantly in the development of coherence optics, particularly for the application methods. So these are we try to exploit this similarity to develop a imaging system. So to realize this kind of interference term are used in the ghost imaging. This is my experimental setup. So if you see here, the object, the GG1, so light from the laser is going through the, I'll first explain the part 1 and then go to the part 2 and 3. So if you see the part 1 is nothing but a conventional ghost diffraction setup, like I presented earlier in the earlier slide. So the light which illuminates the GG1, and if it's rotating or frozen, so the random light now will split into the 2 parts. I will explain why I have taken the PBS1, why not BS1, because I want both beams, reference beam and this beam, simultaneously reach the camera. So the light from GG1 will split into 2 parts. One will interact the object here, spiral phase plate, and it after reflection from the mirror M1, it will move towards the camera CCD1 and CCD2. The another beam you have the which is now reflected from the polarization beam splitter PBS1 will go towards the mirror M2, and then finally again after reflection from the second polarization beam splitter, it will go towards the 2 cameras. But these 2 beams are orthogonally polarized. And since we are doing our experiment on the intensity correlation, we are not doing like I mentioned earlier the Stokes correlation, that kind of thing we are not doing. So our measurement is on the intensity basis. So then there is another beam which was separated by beam splitter BS1 and goes towards the reference, which I represented as a part 2. It will generate a reference coherence function because I have used the MO, and that light will further propagate towards the beam splitter BS2 and goes to the camera CCD1 and CCD2. Since we have the orthogonal basis, so I put the 2 polarizer P1 and P2, and then we get the interference of the light from reference and then object and reference. When I say, because we are having the 2, one reference from outside, another the reference which is not interacting with the object. Like if you see here, U1 is object beam which interacting with object, UR is your outer beam which I represented in the part 3, and U2 is the beam which is not interacting with object, and UR is again the beam, a random field. It's not beam, it's a random field, and it's going through the UR. Okay. Now what we did, if I measure the intensity from these 2 detectors, and I will fix one point in the detector 1 and then remain in the detector 2, or intensity of the pattern of the detector 2, I will move at each and every point and do the correlation. So rather than rotating this ground glass, we have frozen this ground glass and doing the spatial averaging. So we are not doing the like rotating the ground glass and collecting the data in time. We have taken one shot in camera CCD1, another shot in camera CCD2, and then we are doing the average. So using these techniques, we have I will share here the results. You can see that this is a vortex beam, the A, and corresponding phase is shown here in the E. Similarly, we have a few other objects, Chinese character, and you can see the amplitude and phase. We try to also extend this in the microscopy, because if you see the qualities, because we try to image this, the last result D is object taken from the resolution chart, and you can see the quality is not very good. So what we try to do, we try to replace the part 1 by microscopic setup, which is shown in the right hand side as a B, and remaining part of the system is same. So only we have used the 4F system. You can see in the object is the 4F system, and then we try to implement this into the microscope. These are the result for the microscopic implementation of the ghost imaging, and you can see the lower row we are able to reconstruct even the better part. I mean, we can go to up to the line pairs up to 128. So this says that using the ghost imaging, we can implement the ghost imaging technique with the holography and to recover the phase information. Now I'm moving to another part where we try to realize the computational ghost imaging and explain. But these are not, we have not done the experiment. This is only theoretical work. So a computational work. So when we say the computational ghost imaging, so what is the difference between computational ghost imaging and ghost imaging? Let me try to explain. So if you remember earlier slide, here we are having the rotating ground glass, but now this rotating ground glass is replaced by a diffractive element like a spatial light modulator, and using this spatial light modulator, we are giving a random pattern as a sequence. So for each random pattern, we are measuring the correlation, and then this is being repeated. So your spatial light modulator is creating a kind of manipulating a correlation. Okay, so similar idea we have recently, I think 2017, we tried to implement the ghost imaging kind of concept in the holography, and the technique I call the hybrid correlation holography with a single pixel detector. I will explain why I call this technique as a hybrid correlation holography. So in this case, this SLM, so light from the laser, you can see after the collimation from the focusing lens F, and then another lens F. So this collimation setup, light becomes collimated nearly plane wave, and then it goes towards the SLM, spatial light modulator, which is considered to be a reflective type. Just for simplicity, you can also realize you can also use another transmittive type of SLM. So the light which reflects from the beam splitter will illuminate your SLM, and then after reflection, okay, and the SLM is being loaded with a random pattern. So it's a kind of speckle pattern, and this random pattern, which is loaded by the PC to the SLM, will transmit or will be encoded into the incoming beam, and after encoded, this incoming beam, after encoded with a random pattern, it will illuminate your object T, and this object T is a kind of transparency, and then this random pattern, or you can say the stochastic light, is illuminating your structure T, and this light will propagate towards the single pixel detector, and which is kind of is the entire information or entire speckle pattern is being integrated through the single pixel detector D. Now in another arm, because I know what I am giving to the SLM, because every time the random pattern I'm uploading in the over the SLM is being given by the PC. So I know what are the random patterns I have kept in my folder. So each and every random pattern corresponding to the loaded situation, I will digitally propagate, like you can see the bottom portion, and then that digitally propagated random pattern will in random intensity. So after propagation, I'm measuring only intensity, and that intensity, which is digitally propagated, I will correlate with the intensity which was detected by a single pixel detector. An advantage of this technique is that you fix your single pixel detector. No need to move it. What you can do, you need to move only digital propagation. So it is a highly stable technique, because digitally you can move anywhere in the space using proper propagation kernel. Here we have used the angular space propagation method, but you can use any propagation method to digitally propagate the random pattern from the source plane to the detector plane z equal to 0. Here I said z equal to 0, but you can also move here and there. I'll show it. So when I go to the different plane, I see one object. When I go to another object plane, I see the another object. So it gives me the idea of the 3D reconstruction. So now question is, what is basis of this imaging approach, a single pixel holography approach? So the random pattern which I represented here, I can find the correlation, and if you see the correlation here, correlation you are getting the modulus square. So I will also try to give the idea that how to face the recover the complex field in this technique. Okay.
Dr. Singh, can you try to summarize and
yes, just only I have 2 slides.
One for questions, so that I think some viewer audience might have questions. So
okay, I have only 2 slides.
Sure.
Okay.
Thank you.
Okay, so this is the optical channel, what I just tried to explain it. So you have the information, and that information goes to the detector, single pixel detector, and you integrate it. So what you get almost nothing. Everything is scrambled. So you have all information of the object is mixed. Now this complex field or intensity, you are correlating with the digitally propagated. And as I mentioned earlier, that digitally you can propagate anywhere, either z equal to 0 or minus z1 or z2, and then try to correlate this. So when I go to z equal to 0 plane, I see the object 0. When I go to z equal to minus 200, when I say minus 200, it means digitally propagated intensity is here at minus z1, and then correlated, means minus z1 is 200, and then correlate. If you go to positive, you are here, and then correlate. So when you correlate, you get the reconstruction of the object. And like in the ghost imaging, you can increase the quality of the imaging if you take the more averaging. We very recently we tried to extend this for the complex field, and if anybody is interested, I will suggest them to read this paper, how to recover the complex field in the single pixel correlation holography, hybrid correlation. So with this, I would like to conclude my talk. So I tried to explain the correlation based methods, particularly the intensity correlation based Henry-Brown twist experiment and approach, and then how to connect this Henry-Brown twist approach with the different imaging techniques. Thank you.
So let's thank the speaker for an interesting application of the Henry-Brown twist experiments. I'm sure for another 50 years, there will be lots of applications based on Henry-Brown twists that are as interesting as this. Now, we are open for questions. Any questions from the audience?
Excuse me.
Yeah, please go ahead.
Yeah. So can we do imaging of dynamic object with single pixel detector, because updating of random pattern SLM will take some time?
Yes, a single dynamic object is little bit challenging with the single pixel detector, but dynamic object you can do with usual Henry-Brown twist experiment. And if you see here, I have shared one of my papers where I've done imaging of a dynamic object. The paper is this paper. Are you able to see this paper? OptiExpress is this year OptiExpress, and
yes.
So in this paper we try to do the idea is that, see, the advantage of Henry-Brown or the ensemble averaging based approach is that in contrast to usual see, when we talk the imaging through turbulence or random media, people try to usually try to use the adaptive optics. They try to measure it problem or scattering and then try to compensate it. And if you miss few such scattering, your result will be deteriorated. But here we are not worried about measuring each and every. We are doing the ensemble average. So what happens if your object is moving and your camera is fast enough to take one shot, the next shot, and few shots, then you can trace how your object is moving using this Hanbury-Brown-Twist approach. But single pixel we have not attempted so far.
Okay, sir. Thank you.
Any other questions from the audience? Let me just browse if someone is raising their hand. Okay, in any case, it was a very detailed talk with lots of references. So let's thank the speaker for a nice talk. And the audience should contact the speaker by email if they have further questions. Let's thank the speaker.
Thank you.
So with this, we'll conclude this.
Thank you, sir.
Thank you very much. Thank you. So with this, we'll end this session. And let's thank all the 3 speakers who gave excellent talks. Thank you very much.
Thank you.